Okay, so today I thought we'd do a kind of quick one here. Imagine that we have something like a drone or some object, I guess a bird if you're into hunting. Let's say it's moving along at some constant velocity u at a height h above the ground, and that's unchanged. And let's say someone's going to throw a rock or something, some projectile, a ballistic projectile, at this drone, but they're not very good. They throw it directly at the location where the drone is at a particular instant. They don't lead it or correctly account for the fact that the drone is moving. So they aim straight for the drone without accounting for the fact that it's moving. They would miss it, except because they threw it hard enough, it does actually pass up and let's say that it does hit the drone because of the orientation of the launch angle and the speed that it's launched at. Now, it doesn't really matter whether it hits it on the way up or on the way down, but we want to make sure that we do still hit it, accidentally perhaps. And I want to know, what height must the drone be flying? So that's our goal here, is what is this h? If we have a particular launch speed v0 and this particular launch angle theta. Okay, so should be pretty straightforward. We're going to use our usual kinematics equations. In the case of the drone, we know that its position as a function of time, measured relative to this coordinate system where it starts at the origin, where the origin is the launch point of the projectile. We know that, maybe if I call this distance x0, the initial horizontal location of the drone with respect to the launch point, that will have some initial position, and then it will just move to the right at speed u over time t. Similarly, we know that for the drone, it does not change height. So this is just sort of hovering at a constant height. Simultaneously, we know that for the projectile, well, that one is starting at the origin. So I'll have a v0 cosine theta times t for the x component of this velocity. And there's no acceleration in the x direction, so that's it. And for the y component of the position, we know that we'll have a v0 sine theta times t, and then of course the acceleration due to gravity pulling it down. Now for these to cross, to hit each other, we know that they have to have the same x position and the same y position at the same time. So all three of those need to be the same. So what I'm going to do here is I'm going to set these two x's equal to each other, and I'm going to set these two y's equal to each other. And then I'm going to eliminate the time from those two equations. So setting the two x positions equal, we're going to have that x0 plus ut is going to be v0 cosine theta times t. And we can solve this for t pretty readily. Let's see, how do we want to do this? Let's move this piece over, factor out the t, and then divide. So it'll be x0 over v0 cos theta minus u. Now, the last thing we need to figure out is, what is this x0? Remember that this person is aiming directly at that drone at this launch angle. So we've got a nice little right triangle right here. We know that the height is h, meaning one leg is h. The other sort of horizontal leg is x0. And of course, we know that this angle is also theta. So we can figure out how x0 is related to h. And in fact, we can see that the tangent of theta is h over x0. So x0 is h over the tangent. In other words, it's h times the cotangent. Okay, so that's not so bad. We've got our t. Now I'm going to set the two y equations equal to each other, and then I'm just going to plug this t value in for the t's here and here. So let's do that. Okay, so we have our full-on equation with all the stuff plugged in. I want to solve for h. That's my ultimate goal here. So let's notice a couple things. First off, there is an h in every single term. There's an h squared in this term. So I could cancel an h from everything. We also have this common denominator, well, the square of this common denominator with the v0 cosine theta. I don't really want to deal with all that, so I'm going to go ahead and multiply both sides by that value. I'm going to do both of those steps in one go. So multiplying both sides by the common denominator here squared, because remember that part is squared, I'm going to cancel this h and I'll have a 1 times v naught cos theta minus u squared. That's on the left-hand side. On the right-hand side, again, this h cancels out. Sine theta times cotangent is cosine. So I'm going to be left with a v naught cosine theta. And then, because I'm multiplying by the square of this denominator, I'm going to pick up 1 copy in the numerator. And then this second bit here, we'll just have the 1/2 g. One of these h's will be gone, and I'll have a cotangent squared of theta left over. Okay, so this will be pretty easy to solve for h. Let's go ahead and move that h term over here so it's positive. I'll move this term over, and then I'll actually just go ahead and factor out 1 copy of this v naught cosine theta. So what does that look like? Okay, let's make sure we did this right. So this term over here, I factored 1 copy of this thing in parentheses out, leaving the v naught cosine theta. Then this other term I'm subtracting over here, so the minus sign, 1 copy gets factored out. And we can see why that's kind of nice. This v naught cosine theta and this v naught cosine theta cancel. The minus minus becomes a plus u, and then I can isolate my h. So the cotangent squared, when I flip it over, is going to become a tangent squared. There'll be a leftover u here, which I'll bring over and multiply by my 2 from this guy. And then we've got our leftover piece right here. All right. Could do a quick check of the units. This is a speed divided by an acceleration. So yeah, that gives me dimensions. Speed divided by acceleration is not going to give me the right dimensions, but then I have another speed here. We know that speed squared over acceleration does give me the right dimensions for h. We can see it does depend on that initial launch angle. Obviously, if the bird or drone or whatever it is further over or closer in, we'll have to make sure it's flying at a higher or lower value if we're going to hit it at a given launch speed. Or, of course, I can make that launch speed greater if I want to make sure that I'm hitting it at a higher altitude. Okay, I think that wraps this whole problem up. Now, maybe if you're interested, try thinking about, are there any other constraints on here? For example, notice that I can't have h less than 0. That'd be below the ground. So this term right here needs to be at least 0. But that kind of makes sense, right? That's the horizontal component of this launch velocity compared to the horizontal velocity of the drone. You have to be moving faster than the drone in the x direction if you're hoping to catch up to it at all. So that has to be greater than 0. And then, of course, there's some restrictions on these angles theta. For example, if it was straight up, we know that the tangent of 90 is infinity. So there's no chance of hitting it, basically. If you're throwing straight up, it'll move over before you can make any sort of horizontal displacement. Of course, you would have no horizontal displacement in that case. At any rate, this is our final answer to this problem. We found what height this drone would have to be if we're hoping to hit it, even if we aim incorrectly. QED.